I'm saying it so nicely, I'd like to have it on recording. Okay, so class, we're continuing section 8.8, applications of Taylor polynomials. And you saw an application last time where we found a Taylor polynomial to approximate the cube root of x, that function, the cube root of x. And we approximated the cube root of x with a second degree Taylor polynomial, which is a quadratic, about the value a equals 8, or centered at the value a equals 8. And we chose, of course, a equals 8 because it was easy to compute the function and its derivatives at that value. You know, the cube root of 8 is 2. To get the second degree Taylor polynomial, we just found the first three terms of the Taylor series, and then used that to approximate, get a quadratic to approximate the cube root of x. And then we actually used the second degree Taylor polynomial that we found to approximate the cube root of 8.24. Okay, and we recognize that 8.24 is very close to the value a equals 8. Remember, the second degree Taylor polynomial was centered at 8, and so if we use the Taylor polynomial to approximate cube root values of numbers near 8, we should get a fairly good estimate, and we did actually with that. And of course, let me just see here one moment. We also found out how accurate. Well, we asked ourselves if we were considering approximating cube roots of numbers between 7 and 9, how good would the approximation be? In other words, what's the bound on the error? And for that, we used the Taylor's inequality. This is the last recording, the lesson that we had on Tuesday. And and I think people are liking these Taylor polynomials. So what I want to do is I want to do another example with you, where we're going to find the cosine of an angle. Okay, we're going to find the cosine of an angle. So let me just nope, wrong one. Hold on. Hold on here. Let's get it right. Okay. Hold on one moment. Yeah. This example right here. So, we're looking at applications. So we should be understanding why these Taylor polynomials are important. And that's the goal here. So in this problem, what we want to do is we want to approximate the cosine of 69 degrees. Okay, so using a fourth degree Taylor polynomial, and then we're going to ask how accurate is our estimate. So let me give you a moment to copy this example down. And Eric, are you able to hear okay now? Is Eric back with us? Hearing okay? Excellent, excellent. Good, good. All right, let me give you a moment to copy the example down. And of course, I've naturally deactivated your exam and homework, and the reason I do that, it's really out of respect for you, because I don't want students that aren't like attending the class to be working on their homework and exam when you don't have that, because you're in class, you're here participating. So that's why I do that. But all right, let me let you copy the example down. Okay, so here we want to use a fourth degree Taylor polynomial to estimate the cosine of 69 degrees. How accurate is this estimate then? So let me ask, what are nice angles in trigonometry? What are some nice angles? Give me some nice angles that we, okay, 30 degrees, good, Candy, 60 degrees, 45 degrees. Is 69 degrees a nice angle? No, it is certainly not. And so, but yet when you go to your calculator and you type in the cosine of 69 degrees, it gives you an answer. So from a computer science perspective, how is it getting that answer? Okay, well, and how it gets it is there are algorithms in the calculator that are programmed in there to help get these answers. Okay, and Taylor polynomials are a way to help you approximate, get good approximations for answers. So to use the Taylor polynomial, what's the first thing we need to identify? What's the first thing that we have to identify? Okay, and maybe what I'll do, let me just, one moment here. One moment. I want to go, I think I have it, but let me just look real quick here. One moment. I'll just find this here. You know, here's the formula sheet. And remember, if you look in course content in Blackboard, look under Chapter 8 and find Section 8.7. This handout with formulas on it that I made is there as a download for you under course content. And let me just see here, one moment. Actually, I was thinking, hold on here. Yeah, okay. So okay. Here is the Taylor, well, here's the Maclaurin series for the cosine of an angle. Okay, but a Maclaurin series assumes your Maclaurin series is the same as a Taylor polynomial. I want to be careful. A Maclaurin series is the same as a Taylor series centered at what a value? What's the center for a Maclaurin series? Good, Rodrigo. A equals 0. A equals 0. Okay. So the cosine, if we were to use a fourth degree Taylor polynomial, okay? Fourth degree Taylor polynomial for the cosine would be right here, what I'm circling. Okay, that's a fourth, oh, no, actually, hold on, I'm not right. No, the fourth degree Taylor polynomial for the cosine of an angle is right here. 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. Okay. Now, if you wanted to find, for instance, the cosine of 3 degrees, and 3 degrees, by the way, and radians would be 3 degrees times, so we're going to get back to the problem, but we're having a little discussion here that I think is important. We have to convert degrees into radians in order to use the the polynomial here. So, well, pi radians has how many degrees in it? Pi radians has how many degrees? A 180. Good. So think about, here's 180 degrees. And that equals pi radians. So if you are interested in finding the cosine of 3 degrees, you won't use 3 for x. You would use 3 times pi over 180, which is pi over 60. That's what you would use for your x, because you have to have it in radians. Radians are very important. Sometimes people say, well, we don't use radians too much. That's not true. We have to, anytime we use these formulas, like the sine, cosine, we need to have x in, the angle x in radians. So my question to you is, I want to find the cosine of 69 degrees. Now, if I were to find the cosine, if I were to try to approximate the cosine of 3 degrees, would this Taylor polynomial centered at a equals 0 be maybe good? In other words, would this be a decent formula to use? Is pi over 60, is it close to 0? Is it close to 0? It is. It is. It is. Thank you, Michael. It is close to 0. So if you were to try to estimate the cosine of 3 degrees, which is the same as the cosine of pi over 60, right? Well, pi over 60 here is close to a value close to 0. So the Maclaurin polynomial here, centered about it's a Taylor polynomial centered about a equals 0. We could use that to approximate the cosine of pi over 6 and hopefully get a reasonable. We could use that to approximate the cosine of pi over 60, hence the cosine of 3 degrees, and hopefully get a decent answer. But would that work for the cosine of 69 degrees? Okay, would that work for the cosine of 69 degrees? Would it work well? If you convert 69 degrees, that's right, Michael. It's not going to work too well, because if you convert 69 degrees into radians, so you take 69 degrees and multiply it by pi over 180 degrees. Okay, if you compute that, the degrees cancel, right, leaving you with a radian value, which is a number. You're going to get about 1.202, right? So I don't want to use a Taylor polynomial. I don't want to use a Taylor polynomial based off of this series here, this Maclaurin series, because 1.202 is too far away from A equals 0. I mean, I'd have to take a lot of terms in the series in order to get a good approximation. So, I mean, the first thing we have to do here, we know we're going to then, we know we're going to use the Taylor series formula, okay, to get our 5 terms for this 4th degree Taylor polynomial. We're going to use this. But I have to decide what A is going to be. I have to decide what A am I going to choose for my for my Taylor polynomial. What A am I going to choose? Okay, so hold on here. I got to find the problem again. Here we go. So think of it like this. Think of it like this. 69 degrees. You have 69 degrees. What nice angle is 69 degrees closest to? All right, so 69 degrees. That's right, Colombe. It's between 60 degrees, greater than 60 degrees, and less than, what's another nice angle in trigonometry? 90 degrees. Good, Candy. So since so I have to decide which am I going to pick. Am I going to pick the 60 degrees or the 90 degrees? Which angle should I use as my A value? That's right, Candy. Use 60 degrees. Use 60 degrees. Okay, so that's going to be the A that we're going to use. Okay, are there any questions on that before we get to the solution here? Let me ask you this. Suppose you were trying to find the cosine of 49 degrees. Okay, what would your value of A be? The value of A that you use be? Good, 45 degrees. And of course you would convert 45 degrees into radians. Okay, so let's proceed with the problem here. Okay, so since 60 degrees is the closest nice value to 69 degrees, we'll expand our Taylor polynomial about A equals pi over 3. Okay, because pi over 3 is radians for 60 degrees. And remember, if you just take 60 degrees, and I mean, hopefully you know that right off the bat, so to speak. But, 60 degrees, oh, what's it in radians? You take 60 degrees and multiply it by pi radians over 180 degrees, and that's going to get you 1/3 pi. How many has it been a little while since they've done that? Well, no, you've had this in. Okay, so I'm going to give you a chance, of course, to copy, but as you're aware, 4th degree Taylor polynomial requires me to compute 4 derivatives of my function, and then 4 derivatives, and then I have to evaluate all those derivatives at pi over 3. And I have here a little 30, 60, 90 right triangle with the numbers for the legs and the hypotenuse to just kind of help you compute things. We know cosine is adjacent over hypotenuse and sine is opposite over hypotenuse. So All right, let me give you a moment to copy that down. Okay. Are there any questions? Are there any questions? You know, up, like on this part here. Are we? All right. Well, if you're good with that, then let's proceed. So the cosine of x is approximately. This is approximately, right? Cosine of x is approximately. We're approximating the cosine of x, that function, with the fourth degree Taylor polynomial of x centered at a equals pi over 3. And there is the polynomial. So all I did was I took the first 5 terms of the Taylor series. That's what that is. Okay, I'll give you a moment to copy that. Please let me know if you have any questions. Now, incidentally, the fourth degree Taylor polynomial will agree with the function the cosine of x perfectly at what value of x? What value of x will this fourth degree Taylor polynomial, the value of it, would agree perfectly with the value of the cosine? What value of x? So the fourth degree Taylor polynomial approximates, that function is an approximation to the cosine function. But there's one value of x where the Taylor polynomial and the cosine of function their values will agree. And I'm asking, what is that x value? That's right, Colomb. Pi over 3. That's right, because you're centering your polynomial at pi over 3. So if you put pi over 3 in for x, you know, all of these terms here are going to drop out, and you're going to have just a half, and the cosine of pi over 3 equals a half. Okay, are there any questions before I go to the next page? All right. Okay, well, then here's the polynomial. I just wrote it down again. Well, actually, no, I did more than that, didn't I? I mean, if I go back to the previous page, I have to simplify these terms a little bit, you know? Hold on. I have to simplify these terms. I'm not going to leave the coefficients this way, right? So like, for instance, this one here, you have 3 over the square root of 2 divided by 3 factorial. Well, 3 factorial is the same as 6. So that's like 3 over the square root of 2 times 1/6. You know, if you multiply by the reciprocal of the denominator. And that's just going to get you, hold on here. One moment, class. Oh, I didn't write that right. Sorry, I didn't write that right. Let me do it again. All right, so this here, this is square root of 3, sorry, over 2, divided by 6. You're dividing by 6, which is 3 factorial. So you can compute that as square root of 3 over 2 multiplied by the reciprocal. And that's just going to get you root 3 over 12, for example. Okay. So on the next page, you know, that's how, you know, so root 3 over 12, that's how I got that. So I rewrite that fourth degree Taylor polynomial with simplified coefficients. And of course, on your final exam, I would want to see that as well. You know, this material is going to be on your final exam. And now we're ready to approximate the cosine of 69 degrees. But first, I have to write 69 degrees in terms of radians. And 69 degrees is going to be 23 pi divided by 60. And so that's the value of x. That's the value of x that you're going to use. And everywhere you see an x in the formula, okay, everywhere you see an x here, you substitute in 23 pi over 60. And that's what I did here. Okay, let me give you a moment to copy it down. I want to make sure I'm pacing myself well. Let me know if you have any questions. Now we note here, that, you're seeing, of course, 23 pi over 60 minus pi over 3 in every term. So it would make sense. I don't want to subtract that 4 times. Let me just subtract it once and figure out what the difference of those fractions are. Well, pi over 3 is the same as 20 pi over 60. So 23 pi over 60 minus pi over 3 is equal to 3 pi over 60, which is pi over 20. And so I can rewrite. See, I'm going to have to put this in the calculator. I'm going to have to put all of this in the calculator, because that's how, WebAssign is going to want an answer that is reflective of you working it out, and so you have to do that. But 23 pi over 60 minus pi over 3 is pi over 20. So I can rewrite my approximation this way. So the cosine of 69 degrees, which is the same as the cosine of 23 pi over 60, is going to be approximately 1/2 minus root 3 over 2 times pi over 20 minus 1/4 times pi over 20 squared plus root 3 over 12 times pi over 20 cubed plus 148 times pi over 20 to the 4th. This is an important problem. You're almost sure to see one of these on the final exam. And you have to work it out this way, because I'm going to look at the work because I care, and I have to make sure that you understand the concepts. I don't want to send you off into Calculus 3 if you're not good with Calculus 2, right? And just a reminder, I teach multivariable calculus this coming spring. I teach that Math 280 class, as well as Math 282, differential equations, and linear algebra, which is Math 284. So, all right. So now what I'd like you to do is, I'd like you on your calculator to put all of this in on your calculator and see what your answer is. Okay? So take a moment to do that. I want to see, well, I mean, I can tell you, you should get this answer here, 0.3583686. But just take a moment and see if you work it up, put all this in your calculator, and let's see if you get that. And I just want to see if there are a few thumbs ups on that. Okay, so I'll wait just a few moments here. Great, Michael got it. All right, let's see if maybe a few other people get it too, because you should, go through the process. So far Michael got it. But I'd like to see if another student will get it too. So let's see if one more student gets this answer, okay? Okay, did maybe one other person get this answer? The reason I'm sort of focusing on it a little bit is sometimes what happens is, we're getting near the end of the semester and students, they might say, oh man, this problem's kind of hard. I'll focus on the others. I won't worry about this, but it's an important problem. And I want you to do well on the final, and so I want you to, I don't want you to ignore this problem. I mean, this is an application. Okay, so Michael Aloma's got it, but is that it? Is that the only student who's got that answer? 0.3583686? Okay, Rodrigo got it also. Good. Good. All right. So trust me, now here's the thing. Okay, we now should ask ourselves, and it's in the problem. Hold on. How accurate is this estimate? Okay, so we're saying that the cosine of 69 degrees, that's a little bit, let's get it, I can do better than that. We're saying that the cosine of 69 degrees, is approximately 0.3583686. Okay, and now but it's also, since we know that we used the Taylor polynomial to approximate the cosine of 69 degrees, it's a good question to ask, well, how accurate is the estimate? Okay, how accurate is the estimate? I mean, I don't know the true value of the cosine of 69 degrees, but I can at least get an idea of how accurate my estimate is to the true value. And so for that, we have to use, again, it's in the table, it's in your book, it's in the formula sheet. Again, that's if you go to course content, section 8.7, you can download the formula sheet here. But here's the Taylor's inequality. We have to use Taylor's inequality to get an idea of what the bound on my error is in my approximation, and the book calls it the remainder. So, okay, let's talk about it. How accurate is my approximation, t sub 4 of 23 pi over 60? Okay, well, we know by Taylor's inequality the absolute value of the error. We don't care if the error is positive or negative, we just care about the magnitude of it. So the absolute value of the error, or the remainder, which is the difference between the Taylor polynomial approximation and the cosine of x, the bound on the error is less than or equal to m over 5 factorial times the absolute value of x minus pi over 3 to the 5th power. you see we're finding a bound on the air for a 4th degree Taylor polynomial. So then you have, n plus 1 factorial in the formula would be n is 4. So you'd have 5 factorial here. And then this 5 here, well, that, n plus 1 power would be 4 plus 1, that's 5. So now we need to figure out what m is. Well, here's the thing, okay? Normally what you do is whatever derivative you're looking at, you try to establish if it's increasing or decreasing, the absolute value of the derivative, if it's increasing or decreasing. But when we have a sign, or like in this case, the 5th derivative is negative sign. So the 5th derivative of the cosine is negative sign. We say to ourselves, all right, well, the absolute value of the negative sign would always be less than or equal to 1. And so that's what we take the m value to be. So like in your homework, whenever you have you're trying to find an m value for a problem, if the derivative you're working with is a sine or a cosine or a negative sine or a negative cosine, well, the sines and cosines, if the sine waves and cosine waves are never greater than 1 or less than negative 1. So we just take m to be equal to 1. We don't, and that's it. Okay, so that's different. Like the example that we did on Tuesday. Okay, we actually, the example we did on Tuesday, that example, when we found m, we had to take the 3rd derivative of the cube root of x. And that 3rd derivative we discovered was decreasing over the values between, when x was between 7 and 9. And so we put x equals 7 in that 3rd derivative to identify where the derivative was greatest over the interval, and then we let that be the value of m, that value of the 3rd derivative. But in this case, we're just going to let m equals 1. We want m to be easy to get. So, there's 2 ways to get it. But whenever, what I mean is, this is the second example where you had to find m. But again, it's we want to make it easy. So whenever we see sine, cosine, or negative cosine, we just let m equals 1. But if it's a different type of derivative, a derivative that we can see is easily decreasing or increasing, we find m based off of that. So okay, the error in our approximation at 23 pi over 60 would be less than or equal to 1, because that's what we're letting m be, over 120. 120 is 5 factorial, times 23 pi over 60 minus pi over 3. Okay, 23 pi over 60 minus pi over 3, because that x is 23 pi over 60. Okay, that's your value for x. Okay, and we compute that, and we're going to get a very tiny error. We're going to get 0.000000797. Okay, so this is a very good, this is going to be a very, the error in our approximation is very small, the bound on the error. It can't be any greater than 0.000000797. And by the way, that's less than 5 over 10 to the 6th power. And so we can say that our estimate of our Taylor polynomial estimate of the cosine of 69 degrees is correct to 5 decimal places. Okay, we can say that. Okay. On the TI, on your TI calculator, okay, if you were to, okay, so on your TI calculator, if you do the cosine of 69 degrees, so put your calculator in degree mode, but of course don't forget to change it back later. If you do the cosine of 69 degrees, cosine of 69 degrees, what is it on the TI-84 calculator? Can somebody chat it out for me when they get it? Okay, let me see. I got the same thing, Rodrigo. Let me write down what you got here. You got point. Who else got Rodrigo's answer? 0.35. Kahindi did. Thank you, Kahindi. Good, Cologne. Thank you. Thank you, Dan. All right, so 0.3583679,495. Well, let's look at the decimals. Let's look at the decimals. So our estimate, we have we have a 3 in the tenths place. Yep, that agrees. We have a 5 in the hundredths place. Yep, that agrees. We have an 8 in the thousandths place. Yep, that agrees. We have a 3 in the 10,000ths place. Yep, that agrees. And we have a 6 in the 100,000ths place. Yep, that agrees. So this is correct to 5 decimal places. Okay, our estimate is. Okay, how many think that's absolutely cool? I mean, now you know how a calculator can approximate, or a computer can approximate the cosine of these, you know, non-friendly angles. I mean, isn't that cool, knowing that? Uh-oh, I'm not getting a lot of big responses here. I hope maybe. All right, Dan likes it. How many of you have seen the movie Castaway with Tom Hanks, where he's stranded on the island and he has to get himself off the island? Oh my goodness, that can't be before your time. Okay, Rodrigo's seen it. Anybody else seen Castaway with Tom Hanks? That's like a big movie. Okay, Marcella's seen it, and well, now see if I mean someday if you're like Tom Hanks and you're on an island, of course we don't want that, but look, you know, you have the ability to compute the cosines and sines of different angles. That can be useful, right? To help you get off the island, right? I mean, right? That could be useful. You never know. All right, but I don't know if Hanks used Taylor polynomials, I think, but he did use math. I know that. All right, good analogy. I don't know. Do we have a thumbs up on that, or? Okay, thank you, Rodrigo. Let me stop the recording here. Eric likes it too. Good.